In this lab, we had to drop an object straight down and track its position over time. We then had to create a computational model that modeled the effect of just gravity on the object, and another model that included gravity and the drag in order to match our experiment. To summarize my results briefly, I found that the model that only accounted for gravity showed the ball accelerating more quickly, and there were discrepancies when compared to my experiment. This is because drag is present in the real world, and the ball encountered resistance in the air that slowed its acceleration when it fell. Therefore, my model that accounted for gravity and drag was more accurate. This lab addresses the relationship between gravity and the net forces acting on objects, and how these forces can predict motion. This is very important to understand because it explains how all of the objects around us behave the way they do. I'll begin by explaining some of the fundamental principles involved in this lab. The first is understanding Newton's second law and the relationship that mass, force, change in velocity, and change in time have with one another. The next concept that needs to be understood for this lab is gravity, which is defined as the force that attracts a body towards the center of the Earth or toward any other physical body having mass. Universally, you can find the gravitational force between two objects by multiplying negative g, which is 6.7 times 10 to the negative 11th, times the two masses of the objects multiplied together and divided by the magnitude of the distance between the two objects squared, times r hat. However, in this case, we are on Earth, so we can just assume the simplified version of this equation that has already taken into account the Earth's mass and assumes that objects are near the Earth's surface and are roughly the radius of the Earth. Therefore, our equation becomes the gravitational force is equal to negative 9.8 newtons per kilogram, which you can multiply by the mass to find the gravitational force acting on that object. The next concept that needs to be understood is drag, which is a force acting opposite to the relative motion of any object moving with respect to its surroundings. The drag in this case is coming from the air resistance against the ball, as it's being pulled down the y-axis by gravity and is therefore pushing up the y-axis to slow the ball's acceleration. The last concept that needs to be understood is that acceleration equals the change in velocity divided by the change in time. And in the last lab, we learned that velocity equals the change in position over the change in time. Therefore, if the slope of the position versus time graph is velocity, the change in slope will represent whether or not the object is accelerating or decelerating. For my video, as I said before, I captured a tennis ball being dropped from a point of rest straight down. I did not include when it would actually hit the ground because the velocity would change. I'll play my video now. After tracking the ball's motion and collecting data, I found that the ball was falling faster and faster in the same amount of time and was therefore accelerating. I then moved on to my glow script to create my computational models. I began by only accounting for gravity. I input my initial conditions and the ball's velocity could remain at 0 because the ball was dropped from a point of rest. To calculate gravity, this is all we needed. For the actual loop, I kept time under 0.433 seconds because of my last tracker data point and put in the weight or gravitational force formula, so the variable W would equal -1 times the ball's mass times little g times j hat. I recorded this data in a spreadsheet and then moved on to account for drag. I added a drag equation so that FD would equal j hat times the proportionality constant times the magnitude of the ball's velocity squared. Then I added the gravitational force and the drag force to create the net force. I used trial and error to determine my proportionality constant, but eventually found that when B equals 0.0074, the data most closely matched my data from my experiment. Lastly, I added arrows to show the two forces acting on the ball, and you can see the gravitational force is much larger than the drag force, and for this reason, the ball continues to accelerate in a downward direction. I'll play this now. To compare my results, I plotted this all in a spreadsheet where the blue points are from my experiment, the orange dashed line represents my gravity and drag model, and the red line is my gravity-only model. You can see that without drag, the ball accelerated faster, explaining the difference in those two lines. However, the two lines follow the same general path because they both account for the gravitational force is much larger and more significant than the drag force. In all of these cases, you can see the ball is traveling a larger distance with each passing time interval. For this reason, we know that the velocity is not constant, and if you were to plot this on a velocity versus time graph, the slope of the line would be positive, meaning that it's accelerating. If the slope were to reach a plateau, this would mean that the object reached terminal velocity, meaning that it would no longer accelerate. However, this was not reached in this lab, and therefore none of my models show an object at terminal velocity. However, it would only be reached when the sum of the drag force equaled the downward force of gravity, which hypothetically could be reached using the model that accounts for both gravity and drag. In this lab, the ball would have to be thrown and not dropped from rest to reach a velocity high enough to reach this terminal velocity. Overall, this video taught me about how position, velocity, and acceleration all relate to one another, as well as the behavior of objects being acted upon by multiple forces. In the future, I would let my ball fall for longer to try and observe terminal velocity to see how quickly this occurs. I would also try and determine a more accurate drag force because there are bound to be some inaccuracies using my guess and check method to determine the proportionality constant.